Hey guys, welcome to Worms Maths Academy. Today we're going to be looking at the basics of probability. So in this case we're looking at discrete random variables and the distributions of the discrete random variables. So the first thing I guess we need to know is the concept of discrete. When we have something that is discrete, it means that it can only take certain values. By that, I mean, if I flip a coin 3 times, if I said to you, how many heads can I get? We know we could either get 0, we could get 1, we could get 2, and we could get 3. But we can't get any values in between. You can't get half a head. You can't get 3/4 of a head. So when a probability, like when an outcome can only have discrete values, i.e. the number of heads or the number of tails or the number of sixes, etc., we call that a discrete random variable. Or a discrete probability. The other option is if you had a continuous probability. That might be how long it takes students to get to school. And in that case, you could have some students who live on campus, so they're a 0. It takes them 0 time to get to school. You could have students that take 3 minutes. You could have students that take 2 minutes and 59 seconds. And you could have students that take 45 minutes. Because we can take any value over a domain, we call that a continuous distribution. So for this case, we're only looking at probabilities where we can only obtain discrete outcomes. Okay. A random variable is one that you can't predict in advance. So you don't know what the outcome is going to be. I guess the main thing that we need to focus on with probability is if I want to have an event occur, like the probability of 2 tails, or the probability of 3 sixes when I roll a dice 6 times. We know that the probability of something occurring is the number of outcomes that are successful over the total possible number of outcomes. So that's the basis of probability. If I said to you, what's the probability of getting a head when I flip a coin? If I flip a coin, I could get a head or a tail. The number of outcomes that correspond to getting a head is 1 out of the possible number of outcomes, which is 2. So this is the event, a head, and this is the total outcomes, which we call the sample space. And this is the number of them. It's not the probability. So I've summarized here, a set of favorable outcomes is called an event, i.e. our top value, and all possible outcomes is called our sample space. So here, I want to draw a tree diagram and list the sample space when 3 coins are tossed. So the assumption would be, it's a head and tails coin, and it's 50-50. So the best thing I think to do here is to label them. Toss 1, I could get a head or a tail. Toss 2, after I get a head, I could then get a head or a tail. And then on toss 3, I could get a head or a tail. After getting a head, I could get a head or a tail. And after getting a tail, I could get a head or a tail. And then lastly, after getting a tail, I could get a head or a tail, and I could get a head or a tail. We know in this case here, the probability of getting a head is a half, because there's two outcomes and head is one of them. On the second throw, the same occurs. Half, 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 half. Now we want to list a sample space, so they're the possible outcomes. So we follow the tree diagram along the branch. So I can get head, head, head. I can get head, head, and then a tail. I can get head, tail, head. I can get head, tail, tail. I can get tail, head, head, tail, head, tail, 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 head, and tail, tail, tail. What you'll notice is we have 8 outcomes. Now, in those 8 outcomes, we've got 3 heads. We've got 2 heads and a tail, 2 heads and a tail, 2 heads and a tail. So when it's a discrete random variable, what we're doing is we're assigning a value to x. And x is either the number of heads or the number of tails. So if I said it's x is the number of heads, if I said what's the probability that x equals 0, that would mean that I have 0 heads, which occurs 1 out of 8 times. If I said what's the probability that x equals 1, well, I want to have 1 head, which happens 3 out of 8 times. I want to have 2 heads. Well, that happens, 1, 2, 3 out of 8 times. And then lastly, if I want to have 3 heads, because x equals 3, the number of heads is x, well, that happens 1 out of 8 times. So these are our discrete values, the probabilities, like the probability that x is 0, x is 1, x is 2, x is 3. These are our probabilities, and you'll notice when we add those probabilities, they add up to 1. And that's where the concept of a discrete distribution, if they tell you to draw a probability distribution, what they want you to do is put all of your probabilities into a table. And then they want you to give the values of x, that's those little values here, 0, 1, 2, and 3 in this case. I want to find the probability that x is equal to little x. So here, I want the probability that x is equal to little x in this case is 0. So if I said, what's the probability that x is equal to 0, we know that's 1 on 8. The probability that x is equal to 1, we know in this case, the probability that x is equal to 1 is 3 on 8. The probability that x is equal to 2 is 3 on 8. And the probability that x is equal to 3 is 1 on 8. So if you add from left to right, it adds to 1. We can say this is a discrete probability distribution because all probabilities add to 1 and all probabilities are greater than or equal to 0. None of these, they can't be negative. Actually, they can only be between 0 and 1. One last thing to note from this. So this is called a discrete probability distribution. Because my outcomes are discrete, and this is all of the possible outcomes. The last thing to note, in this case, I've got 2 outcomes here. I've got 4 outcomes here. I've got 8 outcomes here. You'll notice this is 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. I've got 8 outcomes on this level. If I had a die, 1, 2, 3, 4, 5, 6. I have 6 to the 1 outcomes. Then if I did it again, if I rolled a die again, I would have 6 outcomes here, then I would have another 6 outcomes, 6 outcomes, 6 outcomes. That's 6 squared. I've got 36 outcomes when I roll a die twice. So it's the number of outcomes to the power of the number of rolls to work out your total possible outcomes. In this case, we've got 8 possible outcomes. But you can determine the number of total possible outcomes by putting the number of options that you have to the power of the number of times that you run that option. So if you flip a coin 10 times, you're going to have 2 to the power of 10 outcomes. And that can be useful sometimes, but we'll discuss that further later. Okay, so this is just applying our concept of basic probability. Enrollment records show that a school has 800 students. So we know the number in the sample space is 800. 450 female, 350 male. What's the probability a randomly selected student will be female? So we'll say A is female. The probability of A is the number of A over the number in the sample space, which is 450 out of 800. We can divide them both by 50. We get 9 on 16. So that's just the application of basic probability, this rule. Okay, here's a summary of basics that you need to know with probability. The first one is all probabilities have to lie between 0 and 1. Makes sense, you can't have a negative probability, you can't have a probability of something being greater than 1. The probability that A equals 1, well, that is an event that's certain, something that has to happen. So the probability that there's still coronavirus cases in the world tomorrow, certain. Probability that A equals 0, that means the event cannot happen. So if I said to you, what's the probability that all of the coronavirus cases in the world are eradicated tomorrow completely? Well, that ain't going to happen. It's certain that it's not going to happen. Next, we have the probability of A naught, or you can also call it that dash, we can call it A prime. And it means if I have a Venn diagram and I said to you the probability of A occurring in here is this. Outside A prime or A naught or A complement, they're all the same thing. Together, if I add the probability of A plus the probability of A complement, it has to add up to 1, the whole sample space. So we can say the probability of A is 1 minus the probability of A naught. Another thing that we know is if we have two outcomes, A and B, we call this the addition rule. If I want to find the probability of A or B, what I'm going to do is say this is A and this is B. We know the probability of A is everything that's in A. The probability of B is everything that's in B. The probability of A or B is anything that's in A or in B. But if we add A and B together, you can see that we account for this section, we account for it twice. But we don't want to do that. We only want to find A or B. So what we do is we subtract where they intersect, which then gets rid of the duplication of everything that's contained in the center where they intersect, and that gives us the probability of A or B. Now, the next concept, mutually exclusive, well, kids get this confused all the time. They get it confused with independence. And mutually exclusive and independence, they don't really have anything to do with each other. Mutually exclusive means that two events can't happen at the same time. So if I said to you the event A is on a deck of cards, all of the hearts, and I said to you the event B, A is all hearts, and B is all diamonds. You can't get a heart of diamonds. So getting a heart and getting a diamond, they're mutually exclusive. They can't occur at the same time. If we know two events are mutually exclusive, they can't happen at the same time, then we know the probability that they intersect is 0. So here, the probability of A or B, when there's A, there's B, the probability of A or B, we just add them together. We don't need to subtract where they intersect because they don't intersect if they're mutually exclusive. Independence we'll come to later in another video. Okay, so let's have a look here. One card is chosen at random from a well-shuffled deck of cards. So, well-shuffled, they're just letting you know that it's random. Don't read into that too much. What's the probability the card is an ace? So I want to find the probability that we have an ace. We know the number of aces in a deck is 4, and that's out of 52 cards, which is 1 out of 13. Now the other way you can look at it is you have 4 different suits, and in each suit you have king, queen, jack, 10 down to 1. The probability of an ace, we have 1 out of 13 in a suit. So you could just do 1 out of 13 in a suit. The next one, the probability of a heart, or not a heart, we know is 1 minus the probability of a heart. We know the probability of a heart, there's 13 out of 52 hearts, which is 1 out of 4. So if I say 1 minus a quarter, we get 3/4. The probability of not getting a heart is 3/4. The next one, the probability of an ace or a heart. The probability of an ace, we just found that before, is 1 out of 13. The probability of a heart, we know, is 1 out of 4. If I want to find the probability of an ace or a heart, we know it's the probability of an ace plus the probability of a heart minus the probability of an ace intersecting a heart. Now, they're not mutually exclusive because I can get an ace that is a heart. The number of aces that are hearts is 1 out of 52. So if you think about it, in these aces here, I have an ace of hearts. And in these hearts here, I also have an ace of hearts. So I've doubled up on the ace of hearts. So here we've got 1 on 13, which is also 4 out of 52, plus 1 on 4, which is 13 out of 52, minus the card that I've doubled up on, the ace of hearts, which is 1 on 52. And that leaves us with 16 on 52, which is 4 on 13. So that is the probability of an ace or a heart from a deck of cards. Now, the next one is either a king or an ace. So we know the probability of a king is I've got 4 out of 52, or 1 in each suit. The probability of an ace is the same, 4 out of 52, or 1 out of 13. I can't get a king of aces, so these two things are mutually exclusive. So king of aces is 0. So in this case, the probability of K or A, it is 1 on 13 plus 1 on 13. We don't need to subtract anything because we know they're mutually exclusive. Hence, the probability is 2/13. Okay. So this one here is just trying to use our rules. 500 people are questioned and classified according to age and whether or not they regularly use social media. The results are in the table below. One person is selected at random from these 500. Find the probability that the person regularly uses social media. So we know the probability of yes, we've got 300 out of 500. Which is 3/5. The person is less than 25 years old. We know there's 240 people who are less than 25 years old out of 500. Divide them both by 20, we get 12 on 25. The person is less than 25 years old and does not regularly use social media. So the probability that they're less than 25 and intersex, does not regularly use social media. In this case here, we want to see where they cross over, which is 40, less than 25 and does not regularly use social media. 40 out of 500. Divide them both by 20 and we get 2 out of 25. So that's just using our basic rules for probability. The number of successes out of the total number. Okay, here, a dartboard consists of a square of side length 2 meters, a shaded 1/4 of a circular disc centered at the bottom right vertex of the square as shown. So we know the total area is a square that's 2 by 2. So we say our total is 2 by 2, which is 4. I should have said total area. If a dart is thrown at the square, it's equally likely to hit any part of the square, and it hits the square every time. Find the probability of hitting the shaded region. So we need to find what this area is. The shaded is, it's a quarter of a circle of radius 2. So a quarter times pi times 2 squared, which is just pi. So the probability of hitting the shaded, knowing that we hit every time, is shaded out of the total area, pi on 4. Now, if I said to you, the probability of hitting the board is 3/4. If I then said to you, what's the probability of hitting the shaded region? Well, first off, you've got a 3/4 of a chance of hitting the board. And then you've got a pi on 4 chance of hitting the shaded region. So we end up with 3 pi on 16. So you've got to multiply that first. If I said to you, what's the probability of missing the board? The probability of missing, well, that's a quarter. Because you either hit it or you miss it. And if you miss it, you can't hit the shaded region. So if they give you something like that, where they say, okay, the probability of hitting the board is 3/4, and then the probability of hitting the shaded region, you've got to multiply them because they have to occur at the same time. One thing affects the next. Okay, now this is a probability table or a Carnot map, which can be really useful. When we add downwards, all the probabilities have to add. So these two probabilities have to add to this one. These two probabilities add to this one. And together, when we read from left to right, these two have to add to 1. These have to add to 1. A crosswards has to add to this value and this value. So let's summarize. I probably shouldn't have filled out the table, but it says Simone visits a dentist every 6 months for a checkup. The probability she'll need her teeth cleaned is 0.35. So cleaned is 0.35. The probability she'll need a filling is 0.1. The probability she'll need both a clean and a filling is 0.05. So we put that information into the table, and we know it always has to add to 1. It says set up a Carnot map to show this information. So if we know the probability of a filling is 0.1, the probability of a clean and a filling is 0.05, we know that the probability of not having a clean and a filling is 0.05 because they have to add up to 0.1. Here, 0.05 plus the probability of a clean and not having a filling, which is 0.3. That has to add up to 0.35. We know that this has to add up to 1, so that's 0.65. This has to add up to 1, so that's 0.90. That's got to add up to 90, and that's got to add up to 65. Either way, this here is 0.6. So it says, what's the probability she will not have her teeth cleaned but will have a filling? The probability that not have her teeth cleaned and will have a filling, not have her teeth cleaned, will have a filling, 0.05 or 1 on 20, same thing. What's the probability that she will need neither treatment? So the probability she won't need a clean or a filling. Not need a clean or a filling is 0.6. Now, one of the rules people don't know is if I said, what's the probability of A naught intersects B naught, which of course is in this Carnot map, there's a relationship between the probability of A naught intersects B naught and the probability of A or B. The probability of A or B is what's inside here, assuming this is A and this is B. A naught intersects B naught is everything that's outside of them. So we can see the probability of A or B is 1 minus the probability of A naught intersects B naught. So if everything in here is equal to 1 minus everything that's outside. And conversely, if I say what's the probability of A naught intersects B naught, well, that's 1 minus the probability of A or B. So this rule can be really useful when you have a Carnot map, because they might give you the probability of A or B, but A or B is useless in this table because there is no A or B. However, it's not useless because we know the probability of A naught intersects B naught is 1 minus that probability. So if I said to you, looking at this table, what's the probability of A or B? We know it's 1 minus 0.6, which is 0.4. We could also prove that by the addition rule. We know the probability of A or B is the probability of A plus the probability of B minus the probability of A intersects B. In this case, we're going to say the probability of C or F. That's the probability of C, which we know is 0.35, plus the probability of B, which we know is 0.1, minus the probability of A intersects B, which is 0.05. If we add them together, we get 0.45 minus 0.05, which is 0.4. But you can see that's much faster. So it's a really good rule to know. Okay, so that's the end of the first section, the basics of probability. Next, I will move on to, actually, let's do this question. So this is using the rules that we've just had. Two events A and B from a given event space are such that the probability of A is 1/5, the probability of B is 1/3. So what I always do with this is draw a Venn diagram. And when I draw that Venn diagram, on the outside, I say the probability of A is 1/5, so the whole thing is 1/5. The probability of B is 1/3. It says calculate the probability of A naught intersects B. So A naught intersects B is this here, when the probability of A intersects B is 1/8. Now, if we know we want to find the probability of A naught intersects B, well, in this case, that's the probability of B minus the probability of A intersects B. So it's 1/3 minus 1/8, because 1/3 is this whole thing, take away where they intersect. That gives me the probability of A naught intersects B. And you can see in this case, if we put them both over 24, 8 over 24 minus 3 over 24 gives us 5 over 24. The next question says, calculate the probability of A naught intersects B when they're mutually exclusive. So knowing what mutually exclusive means, well, we know they don't intersect. So A naught, if there's A, there's B. A naught is everything that's not in A. Where does that intersect B? Well, in this case, it's just the probability. It's just the probability of B when they're mutually exclusive, which means it's just 1/3. So that one's nice and easy. Okay, I'll see you on the next video, which is conditional probability.